this video, we are going to discuss about multi-rate signal processing. So, in this signal processing, many systems will have a single sampling rate. Such type of systems we call it as a single sampling rate system. And some systems will have more than one sampling rate. So such type of systems will be used for processing and digital signals. Such systems will call it as a multi-rate digital signal processing systems. So even that multi-rate systems sometimes we may also called as sampling rate conversion. But here in multi-rate signal processing can be used in many applications such as digital audios and can even in communication systems, in speech and audio processing systems, antenna systems and radar systems, etc. Basically, if you consider an application like digital audio, here for broadcasting we are going to use 32 kilohertz, and for 44.1 kilohertz for an compact disc, nothing but your CD to record any audio in an CD. It will be having a sampling rate of 44.1 kilohertz, and whereas coming for an audio tape, um, it takes an sampling rate frequency of 48 kilohertz. So this particular in application we're going to have many sampling rate sampling rates in particular one application. So this type of system you can consider it as a multi-rate systems, sorry. So to convert this multi-rate are used to improve the performance. uh, so all these are the advantages of this multi-rate signal processing. What are the advantages means? So computational complexity is less, and storage for filter coefficients is less, and finite arithmetic effects are less, and sensitivity to filter coefficients length is also less. So as we have discussed about the advantages, so now we will see how the multi-rate signal processing can be done. So as in one system we are having more sampling rates, so we have to convert from one sampling rate to another sampling rate. So that process will be done by two things. Those are decimation and interpolation. So as you can see here, the in decimation, it will be decimation is used for decreasing the sampling rate of a signal with some factor, and interpolation can be used to increase the sampling rate of a signal with some factor. So now first of all we are going to see about the decimation part. So as you can see in this particular slide, decimation means the sampling rate will be reduced with a factor of d. So but in the class we have discussed with a variable of capital M, so no need to confuse here. So I'm calling it as in capital D instead of capital M. So simply we are saying that with an capital D factor we are going to reduce the frequency. So as you can see here, fx to fx by d. So here as we are talking in terms of the frequencies, the frequency is going to reduce by a factor of d. That's why we are representing that as an fx by d. So how that can be reduced, how that frequency can reduce from fx to fxd, so that we can see with an example. So as we can see, as we consider the capital D, sorry, here capital M is there, capital D is equals to 3. So I want to reduce the x of n signal with an factor of 3. So what we have to do is to reduce with an factor of 3, I have to take the d minus 1 samples. Here d is equal to 3, right? So 3 minus 1 is nothing but 2. So every alternative in every samples, so in every successful samples, so we have to remove 2 samples, so we have to discard 2 samples. So as you can closely observe at this 0.2 and the next point in an y of n. So as you can observe, x of n is the input signal, y of n is the output of your decimation or downsampling part. So as you observe in the y of n and x of n, closely observe the point between 0 to minus 1. and to the x of n, the two samples are missing in between each and every successive samples. So how as we are discarding the d minus 1 samples, the rate will be reduced from fx to fx by d. So here fx by, so as we have written here, and you can observe that this the vibe uh, hd is nothing but the anti-aliasing, so that will be discussed later. So now, as you can observe here, the if you find the frequency domain representation of a downsampling, the 1.6 will be the following equation for that. So as we can observe this following equation, so by this equation we can represent the spectrum of an downsampling one. So as you closely observe this equation, 1 by m summation k is equal to 0 to m minus 1 capital X of e power of j of omega t minus 2 pi k by capital M. So this is the equation of y of e power of j omega t. So now as you observe this equation, so the above graph represents your frequency response of your input signal, and whereas the second graph represents your frequency response of your uh, downsampled signal. So that is nothing but your 1.6 equation. So as you can observe here, so you can observe we're going to have, so m samples, so 0 to m minus 1, so for the summation of 0 to m minus 1, so we're going to have m samples uh, in this particular frequency, in this particular graph we're going to have an m samples, um, m samples of m times the input is going to repeat here. So as you can observe, capital X of e power of j omega t e minus 2 pi k by capital M. So that is y of e power of j omega represents the sum of capital M uniformly stretched and shifted version of x of e power of j omega scaled by a factor of 1 by m. So so as you can observe here, the at this particular part, the input at this particular input we're going to have an pi by m. So if that pi by m if the frequency is the cutoff frequency of that particular signals is nothing but your pi by m. So what happens if that frequency crosses this pi by m? So if that will be done, the aliasing will be affected. So to reduce this effect of aliasing, so we are going to introduce the low pass filter before the downsampling one. Here we have to observe why we have to insert an low pass filter before the downsampling one, not after the downsampling part. Before the downsampling, because um, uh, as the input signals frequency has to reduce or band limited to pi by m. So if to reduce the or if to band limited the input frequency to pi by m, so we have to apply that low pass filter at the input of your downsampling part, not at the output of the downsampling. If you apply the downsampling of the downsampling part, output of that downsampling, result will be 0. Okay, so this is about your decimation part. So the combination of the downsampling and the low pass filter, or we can call it as an anti-aliasing filter, we call it as an decimation. So what we have learned about reducing the number of samples by discarding the d minus 1 samples, all that belongs to the downsampling part. And to remove the aliasing, we are applying the low pass filter. That will comes as that we are talking about as an anti-aliasing filter. So both the combination of these two will call it as an decimation. And now so this is about the decimation part. And now we are going to see about interpolation. So now in this interpolation, the quite opposite part of your decimation here. So the interpolation also will be the combination of two things, anti-imaging filter and an upsampling part. So as you can observe here, up arrow with an L, so that represents that it increases the frequency by a factor of capital L. So here what we are going to see here, what we are going to learn is, so here we are going to increase the frequency. So the in x of n and the w of m represents that x of n will be the input of your upsampling part, and w of m will be the output of your upsampling bar, and the frequency will be increased by a factor of capital L. So how to increase the frequency by a factor of L? Nothing but by inserting L minus 1 0 L minus 1 zeros in between the samples. So by introducing the L minus 1 zeros in between the samples, so automatically the frequencies will be reduced, and by applying some filtering process, that zeros will be rounded off to your um, a non-zero integer something else. So all that matters will be discussed in another upgrade classes, so not now. So an upsampling operation to a discrete time signal x of n produces an upsampled signal y of m according to this particular equation. So as you can observe here, um, so as you can observe here, sorry, so this equation what you're looking at is nothing but the frequency domain representation of an upsampling can be found by taking their transform. So this is the equation as you have can observe. So as you are observing here, it is also should limit the frequency based on pi by L. But here as you can observe, x y of e power of j omega t is equals to capital X of e power of j omega capital T capital L. So that means, so in this particular spectrum of your interpolation or upsampling interpolation, so the some images will be formed. So to remove that particular image, so as you can observe here, above that pi by L to here between this and that, all that are comes under as an images. So to remove that particular images, we are going to um, use this low pass filter after the uh, upsampling part. So why we have to go for then after the upsampling, not before the upsampling part? Because low pass filter will act as an anti-imaging filter. The images will be formed at the output of the upsampling, not at the input of the upsampling. So we have to apply the low pass filter at the input of the output of the low pass filter. To remove all the images, we are going to use this anti-imaging filter, and that is the equation, and this is that equation what we are discussing about the upsampling. So y of m is equals to x of n by L. We are going to represent it as an x of n by L. There in decimation or in downsampling, we are going to represent it as an x of nd. Y of n is equals to x of small n capital D we are going to represent, but in upsampling we are going to represent it as an x of n by capital L, where plus or minus L plus or minus 2L, and y of m is equal to represent 0 otherwise in that equation. So there you can observe here. So y of m is nothing but the output of your imaging filter. So that is about your interpolation. So now, sorry, I forgot to say this. Interpolation is nothing but the combination of upsampling and an anti-imaging filter also, and also the sampling rate conversions can be done by a rational factors also, L by D. So not always the frequency is going to be in round of integer, so it may be an factor also. L by D can be achieved by fast performing interpolation by the factor L, and then the decimation of the interpolator output by a factor capital D. In this process, both the interpolation and decimation are cascaded as shown in the figure. So as you can observe here, upsampling is followed by the filter, and then the filter is followed immediately and then with an downsampling part. So the first two things, upsampling and filter, will call it as interpolation, and filter and downsampling will call it as an decimation. So as you can observe here, the first filter is nothing but your HU of L represents your the anti-imaging filter with an cutoff frequency of pi by L, whereas the second filter is nothing but we are going to use to remove the aliasing for the downsampling part, acts as an anti-aliasing filter, and the cutoff frequency for this filter is nothing but your pi by D or pi by M, what we can call it as. So pi by D. So now as we are following up to this both these equation, both the filters, it is not necessary to use the two filters in an stage wise. So we can cascade these two filters as a single filter. So that single filter we can use as an which acts as in both anti-aliasing and anti-imaging filter. And we have to decide what is will be the um, cutoff frequency for that such particular filter, whether it should be in W pi by L or pi by M. So that will be the minimum of pi by L or pi by M. So the cascaded filters cutoff frequency will be the minimum of pi by L, pi by M. And here in this particular graph, as you can see the example for that, first of all we are going to interpolate by a factor of capital L, and then we have to go to decimate by D. And then by using this example, we have taken capital L as 3 and a capital M as 2. Again I am saying capital M is nothing but your capital D, what we discussed earlier. And this is the example. So first graph, as you can see, this is your x of n, and the second equation represents your W of k. Means it is been the frequency has been increased by n 3. So at 3 means L minus 1 means 2. So 2 samples has been introduced in between every 2 samples. So 2 zeros has been introduced. So according to this graph, by some filtering process, these zeros has been raised to an relevant non-zero integer values. So after that, that particular v of k has been reduced to a by a factor of 2. So capital M is equals to 2. So my capital M is equal to 2 means, so we have to reduce, we have to discard the m minus 1 samples in between this particular sample. So m minus 1 means 2 minus 1, and to one sample we have to remove that. So between this 0 and 1, there is one sample have been removed in this particular, and finally we got the signal of y of m is nothing but your reduced sampling rate reduced by a factor of L by D. So this is the cascading. For this particular slide, we're going to have some examples of this particular cascading part. And thank you.